Kia ora and welcome to this video going through question 1 of the Level 2 Algebra paper from 2015. I'm going to work through each problem here. I suggest if you have trouble reading it on your computer screen, you might want to check the resolution that you've got your YouTube videos set to. The other option is that you go and print out the exam paper from last year and have that in front of you. So some students might find this a little bit hard to read, but hopefully it will all be okay. Right, question 1 is to find the value of the log to base 2 of 1024. So let's start by writing it out like this as an equation. And then what we're saying here is 2 to the power of x equals 1024. Okay, so with logs, they work like this. Okay, 2 to the power of x is 1024. So working with our powers of 2, we can figure out here that, oops, where's my pen gone? X equals 10, right? Anyone who plays 2048 should know your powers of 2 pretty well. Next question, so that's a little achieved question, that first one, and so is this one. So solve the equation log to base 4 of 3w plus 1 equals 2. So again we go 4 to the power of 2 equals 3w plus 1, 16 equals 3w plus 1, 3w is 15, w equals 5. Right, so an achieved tick for this question. Alright, this is the first of the excellence questions in this first question of the paper. Lucas says that the equation the log to base x of 4x plus 12 equals 2 has only one solution. Is he correct? So we must answer that question in your final answer. So we've got x squared is equal to 4x plus 12. So we have x squared minus 4x minus 12 equals 0. We can factorise that easily and we get x, and we're going to have a plus and a minus. So let's have a look. We want to have minus 4x, minus 6 and plus 2. Remember, you can do that on your graphics calculator if you must, but that's pretty unforgivable for a quadratic that simplifies, that factorises so easily. Now, the interesting thing here is we get two solutions. We get x equals negative 2 or x equals 6. But what we're looking at here is we are looking for x being the base of a log, right? And we need to have x strictly greater than 0, right? Logs aren't defined for negative bases. Okay, they're only defined for positive bases, so we need to have just one solution. So x equals 6, one solution. Luke is right. Okay, now that is an excellence question with also with achieved and merit ticks along the way. Right, and the next question is also an excellence question. Right, make x the subject of this. So a to the power of 2x equals b to the power of x plus 1. Now, don't really like those x's being up in the power, so we will start by taking logs of both sides. So the log of a to the 2x equals the log of b to the power of x plus 1. Notice that I haven't put in a base here or here. It doesn't matter what the base is as long as it's the same one. Okay. So, using my log rules, I have 2x log a equals x plus 1 log b. Now let's expand out this side and we get x log b plus log of b. Now we're going to collect up like terms, so this log b here and log a, this is just a number. So collecting up the x's, we've got 2x log a minus x log b equals log b. And here I've got x as a common factor, x times 2 log a minus log b equals log of b. So the last step, which I'm just going to squeeze in on this slide, is that x is equal to the log of b divided by 2 log a minus log of b. Right, so that's an excellence mark for getting all the way down to there. Right, last question. Right, read it carefully through before you start. The market value of Sue's house has been increasing at a constant exponential rate of 3% per annum. So it's an increasing at 3% problem since she bought it 16 years ago at the start of 1999. At the start of 2015, it was worth $350,000. So we're working with an equation in this form. This is the exponential growth equation. Let's think about what we know. Well, R is going to equal 1 plus 3%. And we don't know the initial value. That's what we're trying to find out. We know that when t is equal to 16, right? So from the start of 1999 to 2015 is 16. We know that the value was $350,000. Right. So we're solving this equation. 350,000 is equal to A times 1.03 to the power of 16. A is equal to 350,000 over 1.03 to the power of 16, which is equal to $218,108, and that's to the nearest dollar. Right, so we need to make sure we've said what the value of the house was. Right, so we just need to write something like original price is $218,108. Alright, now I'm pretty sure that was an achieved question. No, actually that was a merit question, right? That's probably going to be the easiest merit question in the whole paper. Now on to the second part, which is on the next slide. Alright, a friend also bought a house at the start of 1999 that cost $200,000. Its market value has also been steadily increasing, but at a slightly higher exponential rate of 3.5%. And then you're given the function, which is that the value is equal to the initial value times 1 plus 3.5% to the power of t. If the houses continue to keep increasing in value at the original rates, in which year will they be worth the same amount? So what we're doing here is we're saying this friend's house, 200,000 times 1.035 to the power of t. When will this be equal to Sue's house? Now we need to use what we've just found, which is the initial value. So 218,108 times 1.03 to the power of t. So I'm going to solve those two equations for t. I'm going to start by collecting up similar terms. So this one and this one kind of match. So we'll divide both sides through by this, and we're going to divide both sides through by that. So I'm left with 1.035t over 1.03 to the power of t equals 218,108 over 200,000. Now find to start putting some things in your calculator at this point, and you'll get on this side 1.0905. So that's that side. I'm going to switch on to a new slide now to do the next little bit. Right, so we've got it down to this, 1.035 to the power of t over 1.03 to the power of t equals 1.0905. We can rewrite the left-hand side by noticing that both of those things are to the power of t. I've still got t up in the power and I want to have it down the bottom, so I'm going to take logs of both sides. So t log of that is equal to the log of 1.0905. So t works out to be, doing that on my calculator, well, we get 17.89. Right? So I'm calculating this on my calculator, and then I'm dividing that through by that. So t is equal to 17.89, but I haven't answered my question. Okay, so that's a merit tick at that point, but we were asked, in which year will the two houses be worth the same amount? So we're starting at the start of 1999, so think of that as Jan 1, 1999, and if we go forwards 17 years, that gets me to Jan 2016, and then the 0.89 is roughly 3/4 of the year. So that's going to be sometime in September 2016. So in which year will they be worth the same amount? They'll be worth the same in 2016. Okay, so that's an excellence question. So really the only tricky thing in there is just recognising that you've got to take logs because you're solving for a variable that's up in the power. Okay, I hope that helped and hope it wasn't too long. Thank you very much for watching, and please let me know if you've got any feedback on the readability of the questions.